Let me give you guys some more examples of multivariable limits. So consider this function. Along y equals 0. Put 0 into here. This thing here will then become 0, and then put 0 into here. That will then be square root x squared. Take the limit as x tends to 0. So this thing here, we suspect that the limit is 0 because it's heading towards 0 along y equals 0. So if if a surface is heading towards 0, then consider looking at its absolute value. Because if a surface is heading towards 0, then the magnitude of the surface to the origin will head towards 0. So consider the absolute value of the function. So looking at the absolute value, our aim here is to trap this thing in between two things, and then use the squeeze theorem to show that if this heads towards 0 and this heads towards 0, then what's in the middle will have no choice but to head towards 0. So consider this this absolute value of the function. So let's try and make the denominator smaller. If you make the denominator smaller, for the time being, let's try and make the denominator smaller. To make the denominator smaller, because you've got that square root thing, if you make what's inside the square root smaller, then the denominator will be smaller. Meaning, if you make this is a positive value, it will always be a positive value because you're squaring it. If you remove this positive value here, if you remove it, then the square root will be what's inside the square root will be smaller. So when you square root, what's smaller will even be smaller. So you're making the denominator smaller. If you're making the denominator smaller, then the overall fraction will be bigger. For example, 10 divided by 7, and then 10 divided by 3. Can you see this is smaller? So therefore this thing here will be bigger than this thing here. So concentrate on making the denominator smaller by removing this. So we can say that this thing here will be smaller or equal to this thing here, because I've removed a positive amount here. I've removed this positive amount here, so therefore this fraction should be bigger or equal to this fraction. Well, anyway, currently we are here, so you taking the absolute value of this whole thing here is the same as you taking the absolute value of this, taking the absolute value of this, and this represents the absolute value anyway. So this thing here is pretty much the same as this thing here. So hang on. So these two cancel each other out, telling you that this thing is trapped, is always trapped between the absolute value of y and 0. Because the reason why it's 0 here is because you're taking the absolute value of something. It can't be a negative, so it must be bigger or equal to 0. Well, anyway, we know that this thing is trapped in between here and here. So now take the limit as xy heads towards the origin. So take the limit of this, take the limit of this, take the limit of this, and then we have no idea what this middle thing is doing, but we do know that it's always trapped in between this and this. Well, as x and y heads towards 0, well, here we don't really care about x. We're not concerned about x. So as y heads towards 0, this thing here will be 0, this thing here will be 0. We don't really know what this is doing, but we know it's trapped in between 0 and 0. Therefore, by the squeeze theorem, this thing here will have a limit of 0. So if you look at the surface, if the origin is actually here, so this is your x, y, and z. So no matter how you approach the origin, it will head towards 0 right here. Okay, next example. So find the limit of this as xy heads towards the origin. Well, use polar coordinates. So convert this into polar coordinates. So r squared is this thing here. So we can put this r squared into here. That will then give us this, and put r squared into here. So this thing here will then become this as r approaches 0 from the positive side. The reason why it's positive is because of this. Hang on. you don't really care about r being negative. You only care about it being approaching 0 from the positive side, because when you use polar coordinates, you're really making the circle smaller and smaller, and we don't really care about a negative radius, whatever that means. We only care about r heading towards 0, r heading towards 0 from the positive side, because the radius is approaching 0 from the positive side. We don't care about negative radius. Well, anyway, this whole thing here will then become this, and then remember from single variable calculus, whenever these two are heading towards 0 and they're on par with each other, meaning you can't have something like this. Even though this is heading towards 0 and this is heading towards 0, they're not on par with each other. Whereas this one here, they're on par with each other. So they're heading towards 0 at the same rate. Here you're heading towards 0 and they're on par with each other. Therefore we can conclude that the limit is 1. So if you plot this surface into a graphical calculator, you're going to get this. And then you're actually heading towards 1. You're heading towards 1. No matter how you approach the origin, you're always going to head towards 1. Okay? And last example. So find the limit of this as x and y heads towards the origin. So if you glance at this, hang on, if you look at the highest power, this is to the power of 6, and then you've got x here. So here you should consider approaching this to in the manner of x equals y to the power of 3. So x, well, approach, you just got to, over time you will develop your own technique of glancing at this. You look at this, this is y to the power of 6, you've got y to the power of 3, so consider approaching it in a manner of x equals y to the power of 3. So y to the power of 3 and this y to the power of 3 will give you y to the power of 6. So after a while you will develop your own technique of glancing at this. So what I'm saying here is approach the origin in the manner of x equals y to the power of 3. So which will look something like this. Y to the power of 3 looks like this. So approach the origin in the manner of y to the power of 3. So maybe something like this. So approach this in the manner of x in the manner of y to the power of 3. So so something like this. So approach it in the manner of y to the power of 3. So so let's put this into here. So that will then give us this. Put this into here. That will then give us this. Tidy this up. So tidy this thing up. It will then give you this thing. And then y to the power of 6, y to the power of 6. Factor out y to the power of 6. That will then give us this thing here. And then y to the power of 6 will cancel out with this y to the power of 6. That will then give us this thing here. So the limit depends on the coefficient. Remember we said approach it in this manner. So the limit depends on oh sorry, hang on, it should be, hang on, bear with me, we should not have this. So the limit equals this thing here. So the limit, so when you apply the limit, it will then equal this thing here. So the limit depends on your coefficient of how you approach the origin. So it depends on this k here. The limit depends on the k. So depending on the k, the limit changes. Now if the limit changes, then there is no limit, because it keeps on changing all the time if you approach it depending on this k here. So because the limit is always changing, then there is no limit. Okay, so as you approach this, well, here we said the limit does not exist. Okay.